everyone. Welcome to today's Open Teams community event. Open Teams is the single point of contact and procurement for your open source solution support and training needs. Visit openteams.com or reach out to us at connect@openteams.com to learn more. As part of Open Teams' overall mission to sustain and support open source, we're also sponsoring the Open Source Architect community with the goal of providing a dedicated space for experts to connect and collaborate over their favorite open source tech. To learn more or to apply for membership, visit openteams.com/OSA-community. Today, we have a really exciting presentation and discussion for you on LPython, a new compiler for accelerating Python code, from Andrei Chertik, the project's lead maintainer. LPython is an ahead-of-time optimizing compiler that's able to target multiple backends, including LLVM, C, C++, and WebAssembly. It's a companion to LFortran, which provides similar functionality around Fortran code. As Andrei will describe in more detail, the intermediate abstract semantic representation that both LPython and LFortran use as part of their code transformation flows has the potential to be a common path for optimization of code written in a wide variety of languages. So, thanks again for attending. Please post any questions you might have during Andrei's talk and demo to the Zoom chat or Q&A. For the Q&A and discussion session that we'll have after Andrei's presentation, we can also bring folks onto the audio for direct conversation. So let me know by DM in the Zoom interface if you're interested in that. Otherwise, feel free to just post text questions. We are recording today's event. The video will be posted on the Open Teams YouTube channel once it's ready. Okay, hello, Andrei, welcome. Thanks for being here and for sharing about LPython.
Hello, Brian, thanks for having me.
Really excited for this one. So before we get started with your presentation, let's talk about you a bit. What's your background, education, career? What brought you to where you are now?
My background is in physics. I have a PhD in physics, and then I spent about 9 years at Los Alamos National Laboratory. I was a scientist there, working on many large codes and small codes, methods development, computational physics, a lot of Fortran, a lot of Python, and C++. After that, and that's where I also started the LFortran compiler for compiling Fortran code. And then after that, I left Lionel and I joined GSI Technology. GSI Technology is a very small corporation. They are a chip manufacturer. They have a custom computing and memory chip, and they need compilers so that people can program it. And that's where I've been for last almost 2 years. And we are developing the LPython compiler as the main compiler.
Okay. So when did that was your PhD work, was where you first started working with compilers, and that interest really set the hook for you?
I started my interest started when, as a Fortran user, I have many ideas what I would like the compilers to do, and they were not doing it. And around 2017, I think I was looking into other compilers to see what it would take to fix them to do what I was hoping to do. And then I decided, let's see if I can write one myself. It might be easier. And that's how LFortran started.
Yeah, it's the analogy that, weak analogy possibly that comes to mind. I've been doing a bit of web development on the side lately, is a component library versus building a page from scratch. When you do it yourself, you can really tune it to exactly what you need and what you want. Yeah.
Yes.
Excellent. All right, so let's go ahead and move into your presentation and demo. Go ahead and share your screen.
So let's do that.
Yep, share is showing.
Awesome.
So all yours, take away.
Thank you. My name is Andrei Chertik, and here are all the co-authors. And then we also have a lot more open source contributors. And this work is, my employer is GSI Technology that's sponsoring this work. So motivation. So can we write a Python compiler that compiles fast and generates fast code? And the answer is yes. Here is a benchmark. On the left, you can see a very simple benchmark that uses some dictionaries. And we also wrote the same thing in C++ and compared Clang, LPython, and Python. As you can see, the benchmarks are pretty good in terms of speed of runtime, execution time. And I'll get more into discussing this particular benchmark, because as you know, benchmarking is very hard, and we'll get into it. But let's start with the demo so that you get an idea what LPython is, what it can do, and then I'll resume the presentation and we'll finish it in about, let's say, 10 to 15 minutes, and the rest of the time we can use for discussion. So let's get to a terminal. So once you compile Python, you have an LPython binary. As you can see, the interactive prompt is meant to be used and will soon implement it. Let's take an example. I'd like to start with a very simple example to show how the compiler works internally, which I think is very important to understand because everything else follows from that. So you can, of course, call Python on the Python code, and it will compile it and run it like you would expect. You can look at the AST, abstract syntax tree. In this case, it's identical to Python abstract syntax tree. It's the same thing. Then the next step in the compiler is we transform this AST to ASR. ASR stands for abstract semantic representation. So if I do that, the key that I want you to focus on is the arithmetic operation, 2 times or 2 plus 3 times 5. Here is how it's represented in ASR. You can see every node is typed. So there is a type for every node. And the ASR representation is very high level. It's higher than Python and higher than Fortran. And it's the same representation for both Python and Fortran frontends that we have. So it's independent of the service language. It's also independent of the backends. So that's where we do all the optimizations. And after that, you can call backend. So for example, if you want LLVM, you can call LLVM. Here's the code. If you don't do anything, it compiles it through LLVM to a binary. You can call C backend. So then you get the code, the ASR translated to C, to a high level C. It's not as high level as we would like yet. Over time, we'll make it nicely polished. The goal is to produce C that you would write by hand. But as you can see, it's not bad already. It's a good start. Then let's look at let's say you are having some Python code and you are coding in it, and let's say you make a mistake. So let's see what happens. So let's just call Python on it. And you can recognize we borrowed error messages from Rust. We like how Rust does error messages, so we try to follow the same approach. And in this case, it tells you that the types on the left and right, they are mismatched. It tells you even what the types are, and you have to change it. So in LPython, we follow a very similar approach as Rust. We do not do any automatic casting. So you have to cast everything yourself, just like you would do in Rust for robustness. And you can see the last 2 notes here. If any of the error messages are not clear, please report it, and we'll improve it and fix it. Now, let's go to integration tests. So if I run all the tests, what you see here is we have about 300 tests so far. Every test is a standalone Python file, and we compile it with LPython, we run it, we make sure it runs correctly, and then we run the exact same file with CPython. And the tenet is if LPython can compile it, then CPython also must run correctly and give you exactly the same answer. That's the idea. So LPython is a proper strict subset of Python. And we have support for NumPy. So if you want to understand what we support, go to the integration test and just search for what you want. So let's see NumPy. So you find a bunch of tests with NumPy, and then you can just pick a test and just run it with LPython. In this case, it's not printing anything because it just checks things using asserts. Now, one interesting thing is we also support a subset of SciPy. So you can say, let's open up this example. So it's importing SciPy and then doing some symbolic operations and some printing and some asserts. Let's see if I have it in my history. So if I run this with just regular Python, so it will just call SciPy. So you can see it calls SciPy and print something. Now let's do exactly the same thing with LPython. So now it took the code, it compiled it to ASR, and we have a symbolic type in ASR as a type. And then it called, then it compiled it through LLVM to a binary. So here is the binary. And that binary, it's a very small binary, and it links against a SimEngine runtime. So if I disable this enable SimEngine, if I remove it, you'll get the linker errors because it's missing the SimEngine runtime functions. SimEngine is a C++ library for very fast symbolic manipulation. So what you see here is LPython can actually compile a subset of SciPy. It's a very, I would say, prototype mode. We just got it finished. Our summer student Anutosh just finished it 2 weeks ago, and we'll plan to think of it like a symbolic API. So a very small subset we support directly, and then SciPy itself could, for example, use it and build the rest on top gradually. Okay, and last demo that I want to show you is LFortran. So, and the reason is, I want you to be thinking of LPython like just a compiler that's similar to Fortran or C++ compilers. So here is a Fortran demo. You see exactly the same thing. If I run it through LFortran, it behaves exactly the same way. The AST is different because it's Fortran, but the ASR is identical. You might recognize the symbolic structure here, types and everything. And of course, LLVM is then identical as well. And then to kind of get an idea about what we support today with LPython, we have this demo. It's called FastGPT. It's a GPT implementation in Fortran. And let's compile it with the gfortran first. So now the gfortran is being used to compile it, and if I run it, it's using the old GPT model. It produces some output. Now I'll take exactly the same code, compile it with LFortran. You can see how every file is compiled, it's integrated with CMake, generates a binary, you can run it. And you can see the printing is a little bit different because we don't have a new line yet implemented correctly, or disabling new line, but it produces exactly the same output as gfortran. And now looking at the code, how it looks like for you to get some idea. The GPT-2, here is the main file. So you can see we support structs. We have arrays inside structs, multi-dimensional arrays, allocatable arrays, meaning they can be allocated at runtime. We can load from a file. We do all kinds of array operations. As you can see, if statements, loops, all of this is supported in LFortran. And that means LPython is inheriting the same backends, the same optimizations, and the same features. All we have to do is just hook it up properly into a NumPy syntax. So here is a web page for LPython. You can see we just reached 1,000 stars. We are very happy about it. We wrote a blog post where you can find many more details about benchmarks and how things work. So I encourage you to read it. Here's the link. Here's the blog post. You can see all kinds of benchmarks. You can compare against Numba and so on. Here is the LPython Git repository. And then I want to show you the benchmark I showed you in the slides. When we published it, somebody told us, oh, it's a very bad C++ code. It has to be improved. And he sent us, was very nice, sent us a better code. So we benchmarked that. We rewrote the Python code. You can see the discussion. It's a very long discussion. At the end, I'll just show you the results. Looks like if we use lists instead of dictionaries, then the C++ code can be a lot faster. Here is the timing that we got so far. And here is the timing for LPython, slightly slower, so we will still be working on speeding it up. Here's the LLVM code. You can see one from Clang and one from LPython. It's almost the same. Clang is unrolling it a little more time, so we'll fix it up in due time. So, but I encourage you, if you find benchmark that you don't like, please run it yourself and send us better code, whether Numba or C++ or Python or Cython or any other Python compiler that you like. If you find that we are benchmarking something incorrectly, let us know. We'll improve it. Okay, let's get back to the presentation. And let's just go rather quickly from the presentation. So L compilers, we have two front ends, LPython, LFortran. LPython is a strict subset of CPython. So any LPython code that LPython compiles is automatically a CPython code. So you can reuse all the toolings. As you saw, we require type annotations. And the tenet is we don't want to be slower than C. LFortran is a superset of Fortran. So ideally, eventually, once we get to production, we want to compile any Fortran code. LFortran makes Fortran code interactive. I did not show it to you in the demo. I can show you later. And it's also never slower than C. LFortran competes with other Fortran compilers. So we want to be as fast as we can. And LPython, of course, as well. The intermediate representation, you've seen how it looks like. It's independent of the front ends and back ends. It's as high level as possible, but faithful to the surface language. So we do not lower anything. We represent every single feature. It's raised from the surface language. It's not lowered. It's straightforward and small, and we have many ASR to ASR passes for optimizations and many other things. We have many backends. LLVM is our main backend. We have a C++ backend. We have a WebAssembly backend, and also direct x86 and even Julia backend. We'll add more later, Python and Fortran. The compiler itself is implemented in C++. So there's no Python dependency. It's pure C++ code. It compiles itself in about 30 seconds on my laptop. So it's very fast to develop. So it can compile quickly. When you use LPython to compile your code in debug mode, it also compiles your code very, very quickly. It's very, very fast to compile. And then when you enable optimizations, it has a very fast runtime. We have if you want to see how it looks like in a web browser, this is Fortran in this case. The compiler itself can run in a web browser. So if you modify it and I click on run, you can see that it updated immediately. The color changed immediately. So it's very, very fast, even in your web browser. Okay. And then the tenets of L compilers is fast. We don't want to be slower than C. So if you discover some C++ or C code that runs faster than LPython, please let us know. And we want to improve LPython. Agile development, we are able to fix many bugs very, very quickly in a matter of days. Typically, if it's just a bug with a reproducible example, we are very fast at fixing it. We are low budget. We have a very small team, but a very highly skilled team. It's easy to retarget, so it's easy to write a new backend. For example, the Julia backend was contributed by an open source contributors in about, I think, less than 2 weeks. It's easy to change a surface language, depending on what kind of language you are targeting. But if you can parse it, all you have to do is generate ASR. What you get in return is all the optimizations, all the features, all the array features, all the high language features, and speed of compilation and runtime. And we want to be interactive and binary compiler. What it means, you saw compilation to binaries in the demo. We also want to run interactively, so that like LFortran does, and CPython does. As for example, you can then use it as a Jupyter kernel. And a clear roadmap. We have a focus clean development. So in the short term, the roadmap is we want to port the FastGPT implementation into LPython. That might be the largest LPython application that we'll have. And you saw the demo that runs with LFortran. Everything works. We just have to port it to LPython and make sure it actually runs in Python itself, LPython itself. We want more complete NumPy support. Arrays, that's our main effort, numerics and arrays. But we also want to have a strong support for structs and pointers so that you can use it for any general programming in principle. We have structs already, we just have to make them more robust. We want to make it at least as fast as C++. Currently, we have some benchmarks that are slower, so we want to fix it. We have interoperability with CPython. We want to, currently through our C backend, we want to integrate it with our LLVM backend. And we want to add custom hardware backends for GPU, as well as other. APU is the hardware for my company, GSL Technology. So we want to also have a specific backend for it. And then longer term plans is to bring LPython, LFortran to beta. That's our next big deliverable. And then eventually to production. Currently, they are both in alpha. Alpha means that if you use it, it will break. It's expected to break. And if it breaks, please report it. And be excited that you found the bug. Please report it to us. We'll fix it. Once we reach beta, it will be expected to work. It will have bugs, but it should be expected to work. So we are alpha. Our goal is to get to beta. And we want, so LFortran, we want to compile most Fortran codes, all of them eventually, such as SciPy. We can compile some subset. We want to compile all of it. And of course, modern code. For LPython, we want to compile bigger projects so that people can use it for machine learning, for example, or even writing compilers or any kind of numerics. SciPy, for example, could in principle later on use it. Optimizations, we want to harden and beautify and formalize the ASR, and as well as automatic text generation, both at the ASR level and the surface language level. Well, conclusions. So compilers with 2 frontends, LPython, LFortran, are fast to compile, fast to run. And my own motivation, the way I best describe LPython is that it fixes all the issues that I have or had with Python. Thank you.
Excellent. Thank you. Very, very exciting. So with that overview, now we can turn to Q&A from anybody who has any questions. I think I'll start in. There were a couple that came up in one of the LinkedIn threads about the posts, the posts that we made about the event. And one of the big ones is, how does LPython compare to Modular's Mojo?
Yeah, so the comparison is the way it took me a while to figure out how we compare it as well. I think I figured it out. LPython is a strict subset of Python, and Mojo is a strict superset of Python. So what it means is that Mojo, as far as I understand it, they try to compile all of Python code. You don't necessarily get speed ups, but they will be able to compile it through their compiler directly, independent of Python, independent of CPython. And then they are extending the language with keywords so that you can, if you want to get the top speed, you have to use the extra keywords, such as declaring, maybe, or have a function that's FN. I think they use the keyword for that, and so on. What LPython does is we do not extend Python. We are very, very strict subset of CPython, and consequently, you don't have to change your tooling. Every code that LPython compiles, you can use all CPython tooling. And the downside is that you have to modify your code to run fast. And LPython will guide you. Now in Mojo, I would argue you also have to modify your code to run fast, because if you don't modify your code, it will run faster, but not at the maximum speed. And if you want maximum speed, even for Mojo, the idea, my understanding of it is you're supposed to gradually modify your code to get speed. With LPython, you can follow almost the same philosophy. We have a bridge to CPython. So if you take a large project, you can just bridge into CPython right away. You just write your main program, for example, in LPython, and you bridge into CPython immediately and just leave everything in CPython. And then you gradually port things into the LPython land by typing it. And LPython will guide you with error messages. It will tell you have to type this, type that, type mismatch. You fix it all, you fix your old code. Once it compiles, it will immediately run at top speed, maximum speed.
Is that what the Python call decorator is doing? Is the call into CPython?
Yes, it's a current. Well, yes. So we have a Python call decorator that allows you to call any function from any CPython module, and LPython takes care of converting the arguments. It's on our to-do list to create a Python decorator so that you can just write a function where you have any CPython code inside and you decorate it with Python. That way you don't have to have an external module where you create your let's say you want to use matplotlib to plot. Currently, you have to create a simple module where you call matplotlib from your own script, and then you call it from LPython via Python call. Once we have a Python decorator, I think it might be easier for users to just have everything in the same file. But I would say one of our tenets is to separate slow and fast code. So LPython by default is fast. In other words, you have to type everything, and it does not allow you to call Python code. You have to explicitly tell it, currently with Python call, later on with Python decorator, that this code is CPython, and so it will be slow.
To bypass everything. Right. All right, so we have two related questions from the audience. Combine them together. So one is what will be the rationale, or what are the reasons for using LPython versus Numba, Cython, other accelerators? So I guess, Areg, I might need you to clarify that the phrasing is, what will be the rationale to use LPython versus Numba, Cython, etc., other than extra keywords? In the sense.
No, I think it's a very good question. In fact, I would even make it even broader. Let me go to can you see my screen?
Yes.
If you go to lpython.org, I scroll to the very bottom. We have a list of all Python compilers, and I counted 30 so far. If you find any that's missing, let us know. So you have Mojo, you have Codon, you have Cython, Numba. PyTorch has a Python compiler inside as well. JAX, MicroPython, Taichi, PyPy, Triton. There's many. Pythran. There's so many of them. So the question is, why would you choose LPython over any of these 30? And of course, let's say Numba and Cython might be the closest, as well as Mojo and Codon. I think those would be, I would say, and Taichi as well. Those are, I would say, the closest compilers. Well, so I would say for multiple reasons. So say you have a bigger Python code and you want fast compilation. So that means that, in my opinion, excludes compilers that are written in Python, because it's very hard to get it to run fast. So that right now, LPython typically can only compile small code, so you don't really need that yet, but you will need it. Once you have 1 million lines of codes, you want your code to fully compile quickly. LFortran needs it, for example. And so now we are only competing with Taichi, I think is in C++, and Mojo and Codon. Those are compilers that are independent of CPython, just written in C++. They should be fast. I have not benchmarked them. They should be pretty fast. So that's one idea. The other idea, let's say you don't care about the speed of compilation, but you only care about the speed of runtime. So a lot of these Python compilers, they are speeding up Python. That's their idea, is to just make Python faster. For example, MyPyC or PyPy. But our idea is we are not trying to make Python faster. We are trying to make it run at maximum speed. And it's kind of hard to wrap your head around it because it's Python, and people, or even I think of Python as being slow, but LFortran brings the point home. LFortran, we are trying to be as fast as possible to compile any Fortran array code as fast or faster than other compilers eventually. And so other Fortran compilers, and of course, as fast or faster than C++ compilers. And LPython is kind of competing in the same leagues, let's say. So we are trying to be as fast as C++ or faster. So that also excludes a lot of these. Mojo, I think, and Codon and Numba, I think, and Cython, I would say, are also trying to be as fast as possible. Based on our benchmarks, it looks like we are oftentimes faster than Numba. So I think part of it, so then you might wonder, okay, so why would that be? We don't know exactly, but I think one of the tenets of LPython is that we are very strict in the typing. So we don't do any kind of inference, any kind of type inference. We give you beautiful error messages, but you have to type everything explicitly. So we don't do implicit typing, we don't do implicit declarations, we don't do implicit casting. Everything is explicit. And that means the compiler always knows at compile time the types of everything. The other part of it is that because the internals come from LFortran, it has very good support for arrays and this kind of very fast Fortran style code. It's not designed from Python. In other words, the internals, the types and how the internals work are designed to be able to compile Fortran, for example, very quickly. So I would say Numba, that's for the arrays. And then Cython. Cython is very interesting. It can compile, I think, all your Python code directly into C API calls. And then you can gradually type it to get speed, C-style performance. I would say our approach is different in a way that we compile directly to ASR that's independent of CPython. And then we have all these backends. If, let's say, you choose the C backend, that would be the most comparable with Cython, then what we give you by default, we don't call into Python or CPython at all. So it would be corresponding to the Cython has a mode that allows you to write your code with, I think it's called no-GIL. At least a couple of years ago, that's what it was called. It enforces that your function doesn't call into CPython and it generates C code. That might be comparable. What we do in addition is we have a high-level optimizations at the ASR, and we support a lot of Python features natively. So we have structs. We do Python data classes, but we compile them as structs. We support NumPy arrays. So you write your code as Python code using NumPy arrays and structs and so on, and we compile it to maximum performance. In Cython, typically if your code only has simple, let's say, loops and so on, then I think it might be quite similar. If your code contains any larger subset of Python, then I think we support it better.
Okay. How does the compile, so the LPython compiled, LFortran as well, but LPython compiled codes, if you're interacting with NumPy or other packages that themselves have C extensions, does the compilation process just completely bypass, like, would you basically no longer be using the NumPy internals for those computations, or does it intercall between those?
So when you use NumPy, we support it directly, and we do not call into NumPy. So if LPython compiles your code, and you can use NumPy, currently a subset, eventually we want to support almost or all of it. It doesn't go into NumPy. It goes into our ASR. We have arrays inside the ASR. We do optimizations on it and so on, generate, let's say, LLVM or WebAssembly, whatever you want. It's completely independent of Python and independent of NumPy. Now, if you, the second part of the question was, if you call, let's say if you have a project that uses NumPy but also have a C extensions, how that would work. So Python can call from C. It's called C call, as well as make a function callable from C, then it's C callable. So if you are willing to modify your projects so that LPython can compile it, you can still call into C using C call, and you can call into Python using Python call, and you can use NumPy directly. That runs that's supported natively, and as well as symbolic, so subset of SciPy as well. If you are not willing to modify your code, then you have to call it through the Python call, but it will run slow.
Mm-hmm. So yeah, the machinery is there to make those connections, but you have to
Yes.
wire it up correctly. Another question related, how well does LPython work with projects like Pandas, Xarray, and other PyDataStack, numerical, and related packages?
So we are trying to support the NumPy API, which is an effort to standardize how to use NumPy style packages like UPy and PyTorch and
this the data APIs project, what the work they're doing, or
no, if it's called data, I thought it's called NumPy API, but I could be wrong. But either way, yes. So the idea is we don't depend on NumPy. We just support the syntax that NumPy uses. We currently require you to do from NumPy import things, but it would not be difficult to, or I would say, it would not be difficult to support other packages like PyTorch. So you can do from PyTorch import tensor. So it's a different syntax, different names, but then we could still channel it through our ASR to get the same performance as you would get through NumPy. That's one approach how we can support these packages. The other approach, let's say for PyTorch, is to let PyTorch figure out the types. So they use inference to figure out the types and give us, and we will hook into it at the middle level where they themselves figure out the types, whether Onyx or MLIR or any of their intermediate representations. Then we could hook it up into our compiler, which might be, it's not clear to me what users would like, maybe both. So we are kind of pursuing both, but right now we are focusing on NumPy itself just to get off the ground. But the idea is to be agnostic of it, so that if you have another library that uses the NumPy API, we should be able to use it.
Yeah, I mean, so Pandas, I know the NumPy API, I believe, is part of the broader data APIs project, and as is the data frame API. So that would seem to be one that would be a logical target for close integration.
And so for data frame, we don't have data frame yet in ASR, so we don't support it directly yet, but I think the door is not closed. So if there is interest, I think we could add it.
Okay. So another question in from Victor. What are the challenges in supporting other hardwares, other processors and platforms with LPython?
So currently we are at the very beginnings of it. If LLVM supports it, then it should not be that difficult to support as well. We don't have currently support for a GPU, but we are working on adding it. We have support, so we have prototype how these backends will work. The symbolic API the symbolic example I've shown you, the way it works internally, it accepts some type annotations, in this case symbolic. Then in ASR, those are we have specific types, and in ASR the compiler knows that some variability is symbolic. Then we have an ASR to ASR pass that transforms this high-level representation into direct C calls into the API of the backend, in this case, SimEngine. And so the way we are planning to support GPU and OpenMP and all these backends is in the same way. So we have to understand what array operations and kernels you compile, and then we have an ASR to ASR pass that will transform it into low-level API calls for, let's say, CUDA or Apple M1 Metal and so on, as well as for our custom hardware, which is much more difficult to program than GPU because it's new hardware. So you have a low-level C, you have custom assembly, but all this will happen in kind of two stages, mainly ASR to ASR pass that takes your NumPy array code and transform it into low-level IO, direct IO, and direct kernels and so on for the custom hardware.
Mm-hmm. So you said the ASR, my sense of the ASR is that the goal is to be that universal central path for all of the compilation run through, but it sounds like there's almost like there's interface layers kind of on the incoming and the outgoing sides that you have to, those multiple passes. There's somewhere in the middle is that true core service language and backend agnostic representation, but there's steps to get it to where you can actually.
That's exactly right. And it depends on the backend. So if you, let's say you write a new backend, you can choose to just support all of ASR. It's designed in a way that you don't even need any ASR passes. You can just support everything. But we do provide optional ASR passes, say for array operations. We have an ASR pass that rewrites array operations into explicit loops. Mm-hmm. It's a lot of work. You have to figure out what needs to be, done with what and how to create the loops and so on. You don't have to use it if your backend or hardware supports array operations directly. You just support them directly. But it's a convenience backend in the LLVM. LLVM, for example, does not support array operations directly. So we call these ASR passes because it makes the backend simpler. But it still leaves the door open. If we want to support it directly in the backend, we could. But typically, our experience is it's the backend itself that can be very complicated. And so we are trying to offload as many things as possible into ASR passes because it's much easier for us to maintain.
Mm-hmm. Yeah, the separation of concerns, keep it in the conceptual realm before taking it into the fiddly details of syntax and everything.
That's exactly right. Yeah.
Okay. So one thing I want to make sure we touch. So you said there's a WebAssembly backend. For the past couple of years, PyScript has been a big thing. Talk a bit more about how, if you would, about how LPython runs through WebAssembly, PyScript. Is there any active work there, or is that just something that should be feasible down the line because of the WebAssembly backend? What's the state of that?
Yeah, so I showed you the demo for LFortran. LPython has exactly the same backend. We have the page, but I don't know if I can quickly find it. But it runs in the browser. We just want to create. We want to add it to LPython page more directly. Our main focus right now is on the LLVM backend. We want to get LPython to beta, so that's our main focus. But we have the WebAssembly backend. It's a direct ASR to WebAssembly backend. It does not use LLVM. You could use LLVM as well to get WebAssembly, and that would be pretty complete. But the problem is, if you use LLVM, it's hard to run it in the browser because LLVM is huge and slow to compile. And so, slow to compile itself, but also slow to run. In other words, if LPython uses LLVM, it's kind of slow to compile, especially in the browser. And it's hard to get LLVM in the browser because it's a huge package with a lot of dependencies and so on. So we have ASR to WebAssembly backend. It's a direct backend. And that it supports large subset, but not as many things as the LLVM backend. So if you want the best support, use the LLVM. But the WebAssembly backend, it supports arrays, it supports functions. You saw the demo with the Mandelbrot set, so all that works today with both LPython and LFortran. And the goal is, don't want to spread too thin. So the backend is there. If you want to contribute, anyone wants to contribute, we try to fix up things as we have time, but our main focus is on the LLVM and deliver a beta quality compiler first. And so depth first, and then we'll spread, then we'll finish up all these other backends.
Yeah, that makes sense. Another question for Victor. Is it possible to invoke or call LPython compilation from within Python, similar to what PyTorch's torch.compile can do?
Yes, that's a great question. It is. It's called LPython decorator. So you do from LPython import, I think LPython, you decorate your function. And I think we have a demo in the blog post that we published. It shows example how to do it. And the way it works, we currently use the C backend because we took some shortcuts and we implemented it through the C backend first. That's our next goal. Near-term goal is to make it as an ASR to ASR pass internally so that we can use the LLVM backend as well. So that we don't depend on a C compiler, you can just use LLVM itself. And the way it works, it takes your Python function, LPython function. It currently saves it to a file, runs Python on it, creates the shared library, it exports it creates a Python extension module. It loads the shared library, and then it makes you use it from Python. It's almost identical to how Numba would do it.
Okay. Excellent. Side curiosity. Just for reference, what was your motivating use case for the symbolic capabilities?
to speed up SciPy. So SciPy is very slow, and we first thought, well, 10 years ago, well, let's rewrite it in C++. And so we wrote that library called SimEngine. It's very, very fast. Back then, at least, it was the fastest from everything we benchmarked. That's already 7 years ago. Maybe there is a faster library now. But the problem is, we found out it's very hard to upgrade SciPy to use SimEngine as the core. We exposed it to SciPy. We have it there in the core. You can use it today, but it's very hard to upgrade all of SciPy to use it. It's a lot of engineering effort. And with LPython, I think it will become a lot easier because LPython you can use it almost like a linter. It just at compile time, it tells you right away what types don't match. And if everything matches and LPython compiles it, you know it will run. It might still give you some runtime issues, but it will run. So that's a big deal. And the other motivation is speed. So SimEngine is great at runtime. It does it very fast, but sometimes a lot of these things can be optimized at compile time as well. If you know oftentimes some subset can be optimized and evaluated at compile time. And so LPython gives you the best of both worlds. Stuff that can be evaluated at compile time, it will do at compile time. The rest will be offloaded to the SimEngine backend. And then the rest of your logic runs at C++ speed or faster. In other words, you get the maximum speed of your code while using SciPy syntax. And so what's nice about that is that if you don't care about speed, you can just use SciPy and CPython. If you do care about speed, the stuff that compiled, you can then run through LPython. So it's very compatible with the CPython ecosystem.
Mm-hmm. So was it research, some sort of the physics research work that you found yourself frustrated with the speed of SciPy?
Oh, yes. Well, oftentimes, yeah, there are a lot of applications where the SciPy just takes a long time to run and compile and just using it. And I want SciPy to become a tool and an LPython tool that people can depend on. And oftentimes in robotics, you get very large symbolic expressions. And seconds quickly turn to minutes and hours, and it's very bad. Being able to run at top speed, it just enables so many more applications, and also it's just more robust when you can compile, because you get most of these bugs get caught by LPython at compile time. So if it compiles, you can kind of trust it that it will run. And it might run incorrectly, but at least it will run. You will not get any kind of the typical CPython exceptions that, let's say, a non-type doesn't have append. These kind of error messages are completely extinct because LPython takes care of it at compile time.
Okay. Yeah. At least finding errors sooner in the process. Yeah. Circling back around, the set of benchmarks of LPython and LFortran is quite extensive, and you mentioned the challenges of benchmarking. I know a bit about that. True apples to apples and finding the right code that actually exercises and tests the things you're trying to test. You talk a bit about the particular challenges that you ran into while working on the benchmarks.
It's very hard because we know about LPython and we made sure the LPython part is solid, but it's very hard to then you want to benchmark against somebody else. So let's say Numba. So we write Numba code, and it's very hard to make sure we did not make a mistake, that we use Numba the correct way, we called it the correct way, installed it the correct way, with all the optimizations on the right LLVM versions. If you're comparing different LLVM versions, you get different performance as well. There's so many things you have to get right. And so one approach is just not to do any benchmarking at all. That's the safest approach, but I'm not interested in it. I want to give it into hands of people and please benchmark it. So I rather get into the ring and let's benchmark it. So the best, and so yeah, all the challenges are just to making sure that whatever we benchmark against is using that tool at the best of its ability. And it's very hard because you have to have a lot of knowledge of that tool. So Numba is one thing. Let's say C++, I showed you the example. We did our best. We used the intrinsic C++ hash tables. We tried std map, we did unordered map, we did all these hash tables and other maps that C++ allows. And we tried to pick the fastest. And I think that benchmark is good as long as you use those maps. I think C++ hash tables, I think we are faster than that. Maybe. I mean, it seems to me like it, but if you can prove it otherwise, please do. But then, of course, people found out, oh, but you don't have to use hash tables. You can use just std vector and lists. So that's a different benchmark. But of course, we also upgraded the LPython code to be equal or apples to apples. And then it's a different benchmark with different results and so on. And also with C++, there's multiple C++ compilers, multiple platforms, multiple compiler options. I'm pretty good at C++. We use it internally for the compiler, so I use it every day. I'm pretty good at it, but C++ is complicated. And so making sure you get the absolute best performance, I think we've done the right thing. But again, if we did not, please let us know, and we will upgrade the benchmarks.
You know, each data point is really a research project in and of
Yes.
itself to try
Absolutely.
to chase it down.
Yes. So we are trying to be frank about this and not make, I am not interested in comparing, incorrect benchmarks, comparing the worst C++ code against the best Python code. I'm not interested in that. I'm interested in compiling the absolute best C++ code that you can come up with. And of course, I'm interested in beating it with Python. So that's the challenge for us.
So you've got, looking to the future, you've got LPython, you've got LFortran in flight. Is there a broader you mentioned L compilers as an idea, at least on your slides. Is there a broader L compilers organization, or what does kind of the broader structure look like, and what are the next service languages, if any? Once again you've got the beta plans and everything, what are the next languages you'd like to reach out to and touch?
It's a very good question. I don't want to spread too thin. That's always my motivation. I want to deliver. So just having the two compilers, it's a big piece of pie, so to say. So I want to first get LPython, LFortran to beta, at least, before I even think about having other languages. Well, I thought about it. So I have a prototype of a C compiler, of course. So we use the Clang AST, and but I did not open source it yet. I just wanted to make sure, is this possible? And yes, it absolutely is possible. It works, but to get it from a very simple prototype into even just alpha, it's a lot of work. It's only the front end work, but still a lot of work. You have to get everything done. So if people are interested, of course, I'm happy to collaborate, but I cannot put focus on that. We will, once we reach beta, I would love to have a C compiler and C++ compiler, or a subset of C++. And then we also, I was curious, can you write like a Lisp or a Scheme compiler? Does that even match to is that even possible? It seems that it's possible as well. So it seems we are not tied, as long as the language it's possible to compile it ahead of time, or at least a subset of it. And as long as you are interested in performance and arrays, or you can have structs and so on, but mainly I would say numerical array-oriented computing, then I think we can write a front end. We can do a mathematical front end too. I don't know if there are legal issues with that, but we have the symbolic stuff, so it'll be very easy to just target at least a subset of mathematical itself.
Mm-hmm. Then you just have to have a way, a syntactically valid way to define your types and those.
The types are at the ASR level. They're very robust, and in the front end, you can do almost anything you want. You can infer the types. So, for example, somebody might be interested. Oh, I would like to have a Numba front end. Well, one way to do that is to just have a Numba itself, and then let Numba do all the type inference as it does today, and then hook it into instead of letting Numba generate LLVM directly, let it generate ASR, and then Numba should have exactly the same performance as LPython.
I was more thinking of like something like Lisp or a language that is strongly dynamic. You'd have to have a way to.
Yes. So if it's dynamic, then it's not gonna work. You have to figure out the types at compile time.
Yeah.
Or infer.
Mm-hmm. Indeed. All right, we are up to time. I think we'll wrap. The one thing left I want to ask, call to action. For anyone interested in LPython, LFortran, LCompilers effort generally, how can they get involved, and how should they go about doing that?
Very good. The best way to get involved is send us some pull requests or find a bug and report an issue. That might be the very first step. And because it's alpha, it should be very easy for you to break it. Just use LFortran, LPython on your code, break it. It'll be super simple. Report the bug, and then see if you can fix it. Get in touch with us on Zulip. We have a link on the LPython page, and we'll help you. And then I'm happy to meet over video and get you up to speed. It's very easy to get up to speed to develop an LPython and LFortran. And we also have Google Summer of Code students, although it just finished, but for next year. We also have some funding. So if you're interested in getting funded to work on this, the best way to get started is send us pull requests, get up to speed, and then we'll be very happy to pay you to work on the compilers.
Terrific. In terms of, are the projects to a point yet where you're thinking seriously about documentation and kind of that surrounding, the surrounding assets, or not yet?
Yes. Yes, although our focus is to just get to beta. That's the primary focus. But yes, if there are people interested in helping us with documentation, we have documentation for ASR. Every node is documented. It's not perfect. I would like to make it perfect. And if you are interested in helping us with documentation, oh, absolutely, I would love that.
Cool. Any last thoughts before we wrap?
No, well, my last thought is trial Python and give us feedback. Anything, especially if you break it, be excited that you found a bug and report it.
Very cool. All right. We got here. Terrific. That's all for the event. Thank you so much, Andre, for presenting and answering all these questions. Thank you to everyone for attending. As I noted, the event's being recorded, and so we'll post that video on the OpenTeams YouTube channel once it's ready. Subscribe there to be notified when that goes up. Please check out openteams.com to learn more about OpenTeams and our offerings, and we hope to see you at a future event. Thank you. Have a good one.
Thank you, Brian. Thanks for having me.